Okay, there we go. This should be the last one of this, but then we're also going to do some problems. All right, so independence and disjoint and independence are not the same thing. All right, so what this is saying right here is it's much easier to think about independent events than to deal with conditional probabilities, okay? And what happens is when people start saying, they see the word and they want to multiply, that's fine. You multiply if you have more than one event. If you don't have more than one event and you see the word and, the problem that people are going to have is that means the intersection of the two groups. And then they want to start multiplying. Be careful. Instead, look at the intersection of those two groups and ask yourself, first of all, you see and. How many events do I have? 1 or 2? If you have 2, and means you're going to multiply. If you have 1, it means how many meet the criteria of both of those things happening. If you can find that very quickly on your own, you're done, and it's so much easier. But and for more than one event is going to mean multiply. So when you multiply, you need to ask yourself with common sense, what is the probability of the second event? Has it changed? Okay. When we talk about drawing without replacement, okay, that's what that conditional probability really is. Back in the first day of class when we were sacrificing someone to the dragon, and we pulled someone and said, oh, you get sacrificed to the dragon outside. And what we said is, that person cannot be sacrificed again because they're gone. So we can't sacrifice them again. So that means that when I selected the second person to be sacrificed to the dragon, we were doing it without replacing the first one. And that's what conditional probability is, because the probability has then changed. Be careful, however, because remember when we talked about M&Ms. M&Ms are a great example of when you are going to draw or dealing with probabilities. Back in the days of sampling, you're drawing, but really it's pretty much the same thing as probability here. If you are given percents, especially with M&Ms, if you are given percents, then these events are going to be independent. Because if I pull one blue M&M, unless I know how many M&Ms there are and what the breakdown of the distribution is, I don't know how the probabilities are going to change. If you are given percents, as we said back in the day of sampling, you have to assume that you have the infinite auditorium-sized bag of M&Ms. And if you pull out one blue M&M, it's not changing the probability. However, if they give you the distribution, or it's an assumed distribution like a deck of cards, and you pull one out, and it doesn't say with replacement, then you are talking about conditional probability. That means the probabilities are going to change on the second event. Okay, tree diagrams. I hate tree diagrams. This is what a tree diagram is. It's based off of an event, conditional distribution, and then you've got the and statement here, this and this happening. I hate these things. They're big, they're messy, and we're not going to use them. Unfortunately, there was a question on the last AP test that was, oh, make a tree diagram. And that really stinks because I don't teach tree diagrams. So if you want to know a tree diagram, then you can do a tree diagram by looking at this and figuring out the book. What we're going to do is we're going to use a conditional distribution from a two-way table because it's so much easier and it gives you a lot of this information. Okay, so the last thing here is talks about reversing the condition. When we reverse the condition in two events, it's not necessarily going to happen as you might think about it. So here we are again. Probability of A and B is equal to the probability of A times the probability of B given A. Okay? With this information, can we then turn around and find the probability of A given B? Meaning I'm going to switch the order in which the two events happen. Now, thinking about what's happening here, the probability of B given A is equal to the probability of A and B over the probability of A's in the denominator A. But this is a fraction. And as a fraction, it's a mathematical function, which means I can multiply. So what I can do, change colors here so it looks different, I can take the probability of A and multiply each side by the probability of A. If I do that, I'm going to end up with this statement. The probability of A times the probability of B given that A has happened is equal to the probability of A and B. So, which is conditional distribution. This is the probability of A and B happening. First A happens, and then B happens, given that A has happened. But I can do that algebraically. With that information, okay? Now, this event and this are the same thing. Okay? So then, what happens is, if I would take this statement, the probability of A and B, and if I knew the probability of B, that would give me the probability of A given that B has happened. Okay? So if I knew the probability of B happening, and I found this, then I have the probability of A and B, which means I've switched those two around. And that's something called Bayes' rule, really. And Bay said, oh, look, algebra. All right, what can go wrong? Well, lots of things can go wrong, okay? Don't reverse conditions without seriously thinking about it. Don't confuse disjoint and independence. We got the addition rule, we've got the multiplication rule. Be careful about disjoint. Okay, are these event disjoint or not? Every time that you see or, you add, and then you ask yourself, do these two intersect? Okay, blah, 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 general multiplication rule, fine. You be careful when you are multiplying. What's the probability of the second event? Do not assume independence, because chances are, honestly, it's not going to be independent. Conditional probabilities. Venn diagrams and tables and tree diagrams help organize our thinking about probabilities. Well, no, tree diagrams, I hate them, so they don't help us at all. Venn diagrams are going to be very useful. We'll see that. We're going to use the tables that we're going to create in replacement of the tree diagram. And now we understand more about independence. Ho-ho! That was fabulous. Okay, that's it for the notes. Now what we're going to do, starting on the next video, we're going to start doing problems out of the book. We're going to have one or two of these. We're going to use Venn diagrams, doing early problems. We're going to look at tables, and then we're going to create tables with known information.